Good morning, everybody. Hopefully yesterday went all right. I heard there was some hiccups with the technology. I will do my best to make sure that does not happen today, and hopefully you just started this video, no problems, everything's good. Today was a good day at Avid, and I'm exhausted, and I know what you guys go through, just going through these notes and taking notes and trying to learn new things. I was exhausted today when I got home. So I'm getting a little taste of my own medicine that I give to you every day. Thank you for all that you do and all the hard work you guys put in to work through some of these calculus problems. I know they are difficult. I know this is hard content. I'm proud of all of you. So I'll stop rambling and let's just get to it. We're going to talk about 5.4, which is all about exponential functions. And specifically, we're going to talk about a very special one today. But we're going to get to that in a little bit. We're going to get to that one in a little bit. Well, let's first start with kind of an introduction of what we're going to be doing here. Here we got this function y equals natural log of x, which is not exponential. No, it is not. And the first question that I have for you is, does y equal natural log of x pass the horizontal line test? So if you had all the horizontal line, you could just drag that around on here and see if it does pass that test. And sure enough, it does pass that test. So we can kind of check that off. It does pass that test. Well, what does that mean? Well, that means this function is 1 to 1. And then you're still probably saying, what does that mean if you forgot from yesterday? Well, a 1-to-1 function means that its inverse function is also a function, okay? So if I was going to take this function, and I was going to copy it over the y equals x line. Let's see if I can do that. Make a y equals x line. I'm going to copy it over this line, that it would also be a function, and thus it would pass something called that vertical line test, which you heard about many years ago, okay? So what does it mean? That means it's 1-to-1 function. So can we draw a graph of the inverse? Of course we can. Calculus. What a silly question. So let's graph this inverse. To graph an inverse, you just swap the x with the y. So here I'm at the point 1, 0. So thus on my inverse I'd be point 0, 1. And here I'm at the point e 1. So I'm going to go over to 1 and go up to about e, somewhere around there. And then here I'm getting closer and closer. You can kind of see this pattern here, what's going on without that little curve in there. Sorry about that. But there's a little graph of my inverse function. So can I draw it? Yes, I can. But I cannot write an I. There we go. Okay, so what is the rule for this inverse function? Well, if you look at it, it's definitely an exponential function. So we know it's of the form to the x power. And this one is a special one. It is e to the x power, okay? This is e to the x, y equals e to the x, okay? So now that we know what our inverse for natural log of x is e to the x, because y equals natural log of x and y equals e to the x are inverse functions, what can you conclude about natural log of e to the x? Well, this is a composite function, right? This is taking this e to the x and put it into, this e to the x and putting a natural log of x, and we know that because they're inverses, that would get us an x. It would undo the operations, okay? Because they're inverse operations, they should undo those operations. And vice versa, if you take natural log of x right here and plug it into this x right there, you would get it to cancel off and just give you an x as well, because they're inverse functions. Now, this e to the x function is a super cool function. A long time ago, this dude named Bernatelli, I think his name's Bernatelli, I couldn't find it up here in this math, rule for math, was working with compound interest, right? And he noticed something. If you looked at this, see this formula right here? This is the compound interest formula. This is 1 plus your rate all over the number of times you compounded to the number of times you compounded it, okay? And he was saying, hey, if we compound a number or a rate many times, almost an infinitely many times, he was running into this number all the time. He kept on getting this number 2.7182818, and he said this number seems to be super important. We are going to call this number e, and that's where e came from. And now this number e right here is used in tons of things in mathematics, especially in the world of interest rates and compound interest, specifically continuously compound interest. Any of you that are going to be actuaries or statisticians, things like that, you are going to be using this E a bunch in the future. I want to show you one more thing I think I saw here. Look at this formula. Have you seen this thing of beauty? Look at that. It says E to the I pi plus 1 equals 0. Are you kidding me? How could that be? But this is true. Put this in your calculator right now. Check this out. E 2.71, some irrational number raised to the square root of -1 times 3.14159, some other crazy irrational number. If you take that and add it to 1, you get 0. And it's truth. I mean, it is. This is true. And some people, because of how crazy this is, they call this God's formula. This is proof. They said this is proof that God exists because this formula is out there. So, I don't know. I just want to give you a little history on that. Okay, moving back on. Sorry, we rambled a little bit. Hopefully you fast forward through that if you wanted to. Let's see, where am I going now? Where am I going? There we go, back at it. So, I need to show you something cool about this E function. Check this out. This is theorem 5.11. Some people call 1111. And it says this: the derivative of natural exponential functions let u be a differentiable function of x. Then, if you take the derivative of e to the x with respect to x, check this out, guys, you get e to the x. I know, you probably are all like in shock right now. I'll give you a moment. Are you guys ready? Yeah. Okay, if you're not, just pause. But yeah, this is amazing stuff, right? And if you take the derivative of e to the u and u is something in terms of x dx, well, that's just the same thing. And then you take the derivative of the u, check it out, you take the derivative of the u and multiply it, okay? So if this was like a e to the 2x, you would just say, well, that's just e to the 2x times the derivative of 2x, which is 2. And you put the 2 out in front. So that's, I know you guys are probably still in shock. Just you get up, go for a walk, come back once you're ready, because I know, yeah, this is just amazing stuff. This is crazy. Crazy. And I'm going to prove it to you when you get back from your walk. Right here, I'm going to show you in this proof right here. I'm just going to lead you through it. We're going to prove that the derivative of e to the x is e to the x. Well, check this out. So first, we know that natural log of e to the x is just x, because these are inverse functions, so they undo each other. This cancels that out, and you're just left with the x, okay? Now, we're going to take the derivative of both sides here. Take the derivative of this and this, okay? Now, when we take the derivative of natural log of e to the x, what do we get? Well, we get 1 over the inside, that's this, times the derivative of the inside, which is this, but we don't know what that is, right? We were trying to prove the derivative of this, so we'll leave this as this, okay? And now let's take the derivative of the right side. The derivative of x is just 1, so we're at this point now. So now we got 1 over e to the x times the derivative, which is what we're trying to prove, equals e to the x is equal to 1. Well, let's just get this by itself. So we're going to multiply both sides by e to the x, e to the x. That cancels that off right there. And look at it, lo and behold, check it out. The derivative of e to the x is e to the x. Isn't that just crazy? It is. So in other words, this is Mrs. G says, what you see is what you get. You take the derivative of e to the x, you get e to the x. Now that you know one of the coolest things in calculus, let's use it a little bit down here, okay? I'm gonna try these problems yet, so I'll probably make a mistake here, but you'll see it. You guys are smart. Derivative of e to the 4x minus 3 with respect to x. So remember our formula right here. Oh, it's way too up. It's right here. We're gonna use this one right here. Our u is like our e to the x. So this is how you take the derivative of this. You just rewrite this. So I'm going to say, well, this is equal to e to the 4x minus 3 times the derivative of this. That's going to go over and multiply by this. So derivative of 4x is times 4. So my answer is 4e to the 4x minus 3. See? Not too bad, right? It's not too bad. Okay. Let's try another one. Let's try one more. Not just one. We're going to do more than one. I lied. I'm sorry. Okay, so we're going to do the derivative of this one right now. I got e to the negative 2x. Remember, you just start by rewriting it. Okay, the derivative of anything with an e to the something is e to that same something. And now we just have to take the derivative of this top and multiply it by it. So we're going to take the derivative of the top. Okay, let me think. This thing will drop by a power. So that's x to the negative 2, right? Oh, no, but it would be just x to the 2 because it's already on the bottom. Sorry. x to the 2. That negative 1 that was here goes on in front, so that becomes a positive 2 on top. So we're multiplying it by this. I guess I should move this down here. Right there, should be like that. Okay, so when all things were simplified, what I have is this is equal to 2e to the negative 2 over x all over x squared. There's your derivative right there for that one. How does that look? And then just make sure. Yeah, I think that's good. I think it's good. So this is how you take derivatives of these functions, okay? Remember, just rewrite the function as is, and then take the derivative of the top and multiply it by it. That's really what's going on here. In this next section, before I'm going to show it to you, I'm going to practice it so I don't look silly. I am going to show you how to integrate some of these functions in this next section, okay? So hold tight on that one. Hold tight. Okay guys, I'm ready to do this. We're going to deal with theorem 15 or 5.12, or otherwise known as 5.12, integration rules for exponential functions. Let u be differentiable function in terms of x. For example, u can maybe be x squared plus 4. That's what that's really talking about. So here we're getting the general one. If you take the antiderivative of e to the x dx, well, that's just e to the x plus c. And if you're taking the antiderivative of e to the u being some form of x with respect to u, then you get e to the u plus c. Okay, so we're gonna, you can probably guess, we're gonna use some u substitution on this. And so let's get started with that right here. This first problem, our goal is to make it look like this right here, an e to the u. That's what we want it to look like on the inside. So let's just make this upper thing a u. So we're gonna say u is equal to 2x minus 1. Therefore, du is equal to 2x. Well, when I look in here, I see my dx. Sorry, I should have had that there. I see my dx, and you probably are all saying, well, why didn't you put an x there? That doesn't make any sense. Nope, you're right. It doesn't make sense. So what I was trying to say before I made my mistake is there is a dx there, but there's no 2 in here. So we got to get rid of this 2 here. So we're going to divide both sides by 2. So I have 1/2 du is equal to dx. Okay. Now at this point, I got my dx, I got my u up there, and I can rewrite this whole thing. I'm going to put the 1/2 on in front. So I got 1/2 integral of e to the u du, like that. The du is right here. This is 1/2 du. That's my dx right there. And then this is my u placed up there. So I got this in terms to look like that, which is great. So now I can say the integral of this is 1/2 e to the u plus c, right there. But I'm not done yet. This u is equal to something, right? This u right there is equal to 2x minus 1. So I'm going to rewrite this right now. This is equal to 1/2 e to the 2x minus 1. Keep that 2x minus 1 plus c. So there is my integral of this function. That's what kind of, this is y equals, right? This is my big f of x, my big function right there. So that's integrating this one right here. Let's try some trig functions. Let's make it harder, right? Give it another shot. Okay, so here the goal is we got to figure out what we're going to let u equal to. Do we let u equal to sine of x or cosine of x? Well, the key thing is I always try to start with, hey, let's make whatever's up in this exponent here u. That's what you want to start at. And it might not always work, but for the most part it does almost always work. So we're going to let u equal to cosine of x. If that doesn't work, we'll try sine of x. Okay, so first we'll let u equal to cosine of x. Now that u is equal to cosine of x, we can find du. Du is equal to negative sine of x dx. Okay, remember our goal is to get an x or a sine of x and a dx over here. So I got my sine of x, I got my dx. I just have this leftover negative, so I'm going to bring that to the other side. So negative du is equal to sine of x dx. Okay, and now I'm all set to rewrite this, right? I can say this is equal to the integral with a negative 1 in front. That's from this right here of e to the u du. And from looking at my formula up here, e to the u du is e to the u plus c when I integrate it. So this is equal to negative e to the u plus c. And now I'm just going to plug in what my u equals. And the u equals this right here. So my function turns out to be this, negative e to my cosine of x plus c right there. So that's integrating one with a trig function right here. That's my example 4. One more problem I want to show to you. We're going to do a definite integral. So not only are we going to find the antiderivative of this, but we are going to evaluate it at 0 and 2. Figure out the area under this curve from 0 to 2. So in doing that, what we first want to do is, again, you probably need to identify u in this situation. We're going to probably have to use u substitution here. Let's see, if we made our top e to the x u and we took the derivative of this, the bottom would be 1 plus u, and we have to take the antiderivative of 1 plus u in the bottom. Okay? Now, if the top, what's going on, sweetheart? You're done? Your parents want FaceTime tonight? Oh, nice. Hey guys, I'm going to FaceTime with my parents. They're in Texas right now. So I better get done with this really fast. I mean, I'm going to take my time. Okay, so, but let's say, check this out. If you take the derivative of 1 plus e dx, you take the derivative of that, you get e to the x dx. So I think our goal is to make the whole bottom u. So let's do this. U is equal to 1 plus e to the x. Therefore, du is equal to just e to the x dx. There. That's right there on top. Perfect. And then there's your dx right there. So now we have everything we need to rewrite this thing. This is equal to the integral from 0 to 2 of 1 over u du. And we learned in the last, not yesterday's lesson, but last week, that the antiderivative of 1 over u is natural log of the absolute value of u. Oh, remember guys, this is x equals, right? This is x equals. Don't forget that. Sometimes I forget that. And we're going to integrate that from 0 to 2, but those are both equal to x. Okay, so because these are both equal to x, there's 2 routes you can go. You can take this 2 and plug it into this x here and see what u is. So if I took a 2 and plug it in here, I get 1 plus e to the 2, and that doesn't really simplify down to anything. So I might not change these into u's. I might just change this u back in terms of x's. So let's do that. We've got natural log of the absolute value of 1 plus e to the x absolute value. That's integrated from 0 to 2. Okay, and I just put this back in for that. Okay, so we got that done. Now we're gonna plug this in, figure out what we get, and then subtract it from plugging this in. So I get natural log the absolute value of 1 plus e to the 2, close it off, minus natural log, I'm gonna take this and plug it in for my x, of the absolute value of 1 plus e to the 0, close it off. Okay, I have no idea what natural log of 1 plus e to the 2 is, so I think that's as good as that gets. But I know that natural log of this is this area right here. This is 2 because this thing right here is 1. So my final solution is natural log of the absolute value of 1 plus e to the 2, close it off, minus natural log of absolute value of 2. Now, if you look at these things, both of these are positive, right? That 2 is positive, this is going to be positive. 1 plus an e squared is definitely positive. So we can just say this is natural log of 1 plus e squared minus natural log of 2. But we can bring these into one log, right? Because it's subtraction. So we can say this is natural log of 1 plus e squared all over 2. Now we got it all as one little function, nice and clean and neat. We just box it and call it a day. So there you go. That is how you not only take the derivative of functions of e to the x, like we did up here, but it's also how you integrate those functions as well. Now if you go to your Google page, let's see if I can find it here. Hopefully it just logs me into it. Oh good. I think the assignment for today is right here. It's 5.4a, 297, and it's 37. Are we doing 5 point? Yep. 41 through 51 odd and 89 through 90 odds. Those are the problems that you are going to do today. Copy those and bring them back. Okay, put them in there. There they are. I knew they'd come. Okay. I hope this lesson made sense for you guys. You have a nice long weekend. Jealous. I will be here tomorrow doing some professional development. But you guys have a great long weekend. Get this homework assignment done. Watch any video. If that video didn't work for you yesterday, try to get that homework assignment done as well. You've got an AP worksheet that's due for you next week as well. So you're busy. You're AP students, so you're busy, busy, busy. Keep up the hard work. Proud of all you. And take care. Good night. I mean, it's not night. Good. Have a good lunch is what I meant. It's night for me. It's 8:55 right now. That's what teachers do. They make videos. That's their lives. Bye.